Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. So this is a new problem coming from LeetCode, problem number 22, generate parenthesis. Extremely highly upvoted problem, more than 16,800 upvotes, right? If you see in which all companies this has been asked: Amazon, Adobe, Microsoft, Apple, TikTok, Uber, TripAdvisor, Yandex, Walmart. You can see previously also Facebook, Bloomberg, like all the big tech giants have been asking this question, right? So very frequently asked question, to be very honest. The problem says that given n pair of parentheses, write a function to generate all combination of well-formed parentheses. So you'll be given a value n. Okay, you'll be given an integer value n, and you have to form all combination of well-formed parentheses using n parentheses, n pair of parentheses. So n pair of parentheses becomes 2n, right? So if n is equals to 3, then you technically can take 6 parentheses, opening or closing, and you need to form well-formed parentheses. Well-formed parentheses are whatever number of opening you have equal to closing, and they should be balancing each other. So for example, this 2 balance each other, then this 4 balances each other, and then this 6 balances each other. So this is one valid combination, right? So another valid combination can be this one, can be another valid combination, this can be another valid combination, and so on, right? One invalid combination I can show you, like something like this. This is an invalid combination because this doesn't balance out each other, right? You have a closing parenthesis for which you don't have an opening parenthesis, and you have an opening parenthesis for which you don't have a closing parenthesis, right? If the value of n is 1, then technically the only 2 length parenthesis that is balanced is this one. N can be as big as 8, okay? How can we solve this problem? So one quick piece of advice that I would like to give all of you. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. Is that whenever you have very less constraints, very less like very small bunch of constraints, then technically sometimes recursion can help, right? Because you can see in recursion we try to generate all possibilities. When you see subsets, subsequences, we try to generate all possibilities, that can you include an element or not include an element, and something like this. So when you have scope of generating all the possibilities, because the constraints are a bit less, then also you can directly think in terms of recursion first before moving anywhere else. Okay, so if let's say you have n is equals to 1, the only valid parenthesis is this. If you have n is equals to 2, now we can have more valid parentheses. For example, for 2, you have to always calculate 2n length string, right? So this can be one valid parenthesis, or this can be one more valid parenthesis. Then for n is equals to 3, if you go for n is equals to 3, then you have this, you have this, you have this, you have this, and let's see, you can do something like this also, right? 5, I guess 5 strings should be there. 1 2 3 4 5, right? So you can see we have 5 different possibilities. We have 5 different possibilities. So all we have to ensure is that whatever possibilities we generate are balanced. What are balanced strings? Balanced parenthesis strings, where for every opening you have a corresponding balancing closing parenthesis. For example, if you see, for this opening we have this closing, for this opening we have this closing, and this opening is having this closing. So this is a balanced parenthesis string. This opening has this closing, this opening has this closing, and this opening has this closing. So we have to generate all the balanced parenthesis strings. Actually, you have to generate the string. So whenever you have to actually generate the output instead of counting or checking, then our printing strategy might help. Our printing strategy might be able to help us here. Now, what can be the corresponding logic? If you carefully see, then technically you have to generate a 2n length string. In a 2n length string, there should be n opening parenthesis and n closing parenthesis. Can I say that? We are damn sure about this, right? 3 opening, 3 closing. 3 opening, 3 closing. 3 opening, 3 closing, right? So every time you will be having n opening parenthesis and n closing parenthesis. Okay. So if I write a function, f of n comma o comma c comma output, what is this function going to tell us? This function is going to generate all possible combinations of strings with o number of opening strings and c number of closing strings, such that the final length should be n into 2, right? So if now we write a function like this, f of n comma o comma c comma output, why I am keeping all of this? Because this output is going to be a string in which we are actually going to generate our final output, because this is the printing strategy. O denotes number of opening parentheses used, c denotes number of closing parentheses used, and n denotes the total number of pairs that you can take. So just think about it. Just think about it. If I say that I start generating some parentheses, okay? I start generating some parentheses. Initially, everything is 0. That is, we don't have any opening, any closing. Now just tell me one thing. For every character, I have 2 choices. Can I say that? See, for every index, any index that you pick, I have 2 choices. I can either add an opening parenthesis there, or I can add a closing parenthesis there. Can I say that? I just have 2 character choices, right? for every index, we can either add an opening parenthesis or a closing parenthesis. Can I say that? So what will be one possible way? One possible way is try every possibility on each index, just like our subsequences. Just try every, like for every index, opening, closing, opening, closing, opening, closing, and so on. Right? Or maybe we can do a bit of smart things. What smart things we can do? Let's see. Now just tell me one thing. If I don't have any opening parenthesis, because opening is 0, closing is 0, so can I say we have equal number of opening and closing, right? Whenever we have equal number of opening and closing, can I start with a closing parenthesis? I can never start with a closing parenthesis, right? So if both of these are equal to each other, I can never have closing parenthesis. Can I say that? Right? I can have closing parenthesis only in those cases where opening is greater than closing, right? So here I can only add a opening parenthesis. So I consumed one opening parenthesis, closing is not there, and this is our string. Now I have two possibilities. I can either add a opening or a closing. Both of these I can add. If I add a opening parenthesis, this becomes 2 comma 0 comma this. If I have a closing parenthesis, this becomes 1 comma 1 comma this. Now again you can see here I can still add an opening parenthesis as well as a closing parenthesis. So I have again two choices, opening, closing, both. If I do opening again, 3 comma 3 comma 0, opening, 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 3 comma 2 comma 1, opening, opening, closing, right? Whereas in this case, now I cannot have a closing parenthesis because the whole string is balanced. The further part can only be generated using a opening parenthesis, because you cannot put a closing parenthesis before an opening parenthesis, right? So I can say this check, that if opening is, let's say, greater than closing, if opening parenthesis is greater than closing, then only we can add closing parenthesis. Otherwise we cannot add closing parenthesis. This is for sure. Okay, so from here I'll be having only one choice, that is add a opening parenthesis. Now see this case. Can I say I have exhausted all the possible opening parentheses, because there can be only n opening parentheses, right? So the moment you exhaust all the opening parentheses, from here now you can only have closing parentheses. See, closing, 3 3 2, closing, and 3 3 3, closing. Can I say that? Can I say that? Because once you have exhausted all the opening parentheses, now you can only add closing parentheses, because you don't have any other option. Whereas if you see here, I still have two choices. That is, I can have a opening parenthesis or I can have a closing parenthesis, right? Now from here, if you see here, now opening parentheses are exhausted, I can only have closing parenthesis. So 2 calls only for closing parenthesis. 3 3 2, opening, opening, closing, opening, closing. Then 3 3 3, opening, opening, closing, opening, closing, closing. This is one more combination that I got. Then from here, you can see opening and closing are equal to each other. I cannot have a closing parenthesis. So the best I can do is opening. 3 3 2, opening. Now you can see opening has been exhausted. I can only have closing parenthesis. Right. So you can see 3 combinations I have created here. The other 2 combinations can come from here. Because now here I have two choices. I can have an opening parenthesis also. I can have a closing parenthesis also, because I still have scope for opening parenthesis, and because closing is less than opening, so I can still have closing parenthesis. So this is the agenda that you can keep, that if you have opening parenthesis greater than closing parenthesis, then only you can add a closing parenthesis, right? So I can do something like this. I can say that if opening parenthesis is greater than closing parenthesis, then only I can add a closing parenthesis. So if you add a closing parenthesis, you add c plus 1, and inside your output, you add a closing parenthesis. Otherwise, you check if opening parenthesis is less than n, because you don't want to add an opening parenthesis if you have exhausted all the available opening parentheses, and all the available opening parentheses are just n, then I can say f of n comma o plus 1 c as it is and opening parenthesis. Can I say we just need to make these two calls? That's it. So see, anywhere, if opening is greater than closing, no. So you just have this. So you will check, is opening less than n? Yes. So you add an opening parenthesis. Now here, is opening less than n? Yes. Is closing less than opening? Yes. So both the calls, right? So you just need to make smart calls here. One way could have been that you generate all possibilities, that at every index, opening, closing, opening, closing, opening, closing. So that possibility is there, but you will irrelevantly make a lot of calls, and you will eventually generate some unbalanced parenthesis strings also. So in the base case, you need to manually check whether the string is balanced or not. With this particular approach, I am always just generating the balanced parenthesis. And how I am doing that? If at any point of time you have a string like this is already balanced, right? This is an already balanced string. Inside a balanced string, the number of opening parentheses is equals to number of closing parentheses. So whenever you have a already balanced string, do you think I can add a closing parenthesis? No, I can never add a closing parenthesis on an already balanced string. So that's why I always add a opening closing parenthesis when opening parentheses are greater than closing. For example, this. If opening parentheses are greater than closing parentheses anywhere, then I can definitely compensate it with a closing parenthesis because I have some scope. But here I have no scope. That's why the first check, that if opening parenthesis is greater, then only you can add a closing parenthesis, right? Apart from that, I don't want to just keep on adding opening parentheses, right? For example, if you see here I have exhausted the limit of opening parentheses. Now there is no point of adding opening parentheses. You just check about closing parentheses and add a closing parenthesis. Check closing, closing, check closing, closing. So this is the another check. This is another check. What will be the final base case? Can you see in every base case, when closing becomes equal to n, closing becomes equal to n, closing becomes equal to n, you stop. Because see, opening becomes equal to n very early. When opening becomes equal to n, it doesn't matter, you have generated the whole string. Because if opening is equal to n, it can be a case that opening is greater than c. That is, you still have scope for closing parenthesis. But the moment closing also becomes equal to n, you have your answer. So you can say print output and return. So you can see the simple printing strategy is helping us here, and how we are actually manipulating opening and closing parentheses is helping. We cannot add a closing parenthesis on an already balanced string. So an empty string is already balanced. Something like this is already balanced. Something like this is already balanced, right? So on a balanced string, you cannot have a closing parenthesis. Opening you can add every time, but there is a limit to opening also. That when you have exhausted the opening, then you cannot add opening. So you might think that, hey, sir, why you are keeping the check here? Why not just keep on adding opening? Because this will be a case. So either you keep a check here, and then based on this check, you make a call, or you make a call every time. And in the base case, you can add some base cases. So implementation can change, right? So if I try to code this solution, I say void f, I'll be having a int n, int o, int c, and string output. I will say that if c becomes equal to n, I'll keep a result vector. Sorry, std vector of string result, and I'll say result dot pushback output and return, because here we don't have to print the output. If you carefully see the question, we have to store all the output strings inside a array, or you can say vector, right? Otherwise you will say that if opening is greater than closing, then you can have a closing parenthesis, and if opening is less than n, then only you can have a opening parenthesis. That's it. That's it. So what I'll do before I make a call there, I'll do result dot clear. I'll clear my vector. I'll make a call to f of n comma 0 comma 0 comma an empty string, and at last I'll return result. If you run this piece of code, okay, so we have some issue here. If o is less than n, we do o plus 1. Okay, are we missing something? If o is greater than c, okay, so what we are doing, we are always keep on adding our opening string only. So let's see if there is some problem. We added output, makes sense. Is opening less than n? Yes, so we add an opening, then again opening less than n. Interesting. So we miss out on anything? Function f. So one small mistake we have done here, we have to add a closing parenthesis. I by mistake added a opening one only, and this should be a closing parenthesis, right? Because when opening is greater than closing, then I can add a closing. And one very important thing that you need to keep in mind, you cannot put this in if else. It's not like you are going to put this in if else. Why? Because I'm trying to make all possible calls smartly. It's not like either I will add opening or I will add closing. Because if you remember the diagram, there can be some cases where we have to call both of them, not just opening or not just closing. I can call both of them. So if I have to call both of them, then this cannot be a if else. They have to be separate ifs. That can I call this? Yes. Can I call this? Yes. So that kind of case, let's try to run the code now. Okay, accepted, submit, and done. So you can see in one attempt we have successfully solved the problem, and this is a simple solution for generate parenthesis. I hope the overall logic is clear to everyone.